Okay. So the next vocabulary word is equivalent equations. Equivalent equations, guys, are just two equations, okay, that have the same solutions. Two equations that have the same solutions. That statement, right, that vocabulary word right there, is the premise or the backbone of everything that we're going to do. Okay, when I start with an equation, I give you an original equation, and then you do something to both sides, because you've heard that phrase before, right? And you're going to get a new line, a new equation. They are different. They are not the same equation anymore. However, the solutions to the new one that you just made are solutions to the one you started with. Does that make sense? Or have solutions to the one that you started with. And that concept is the number one concept that I struggle with in regards to my higher level students, my calculus students, my pre-calculus students, the seniors and juniors, okay? Because if they forget that or they don't know that, and then they don't understand the logic of what we're doing as we work through a problem, okay? My hope is, because there's some real weird twists and turns sometimes that we got to work with when we get to higher level algebra, that you can only recognize or realize if you understand that concept right there. As you manipulate an equation, you add something to both sides, you subtract something from both sides, multiply, divide, whatever. The thing that you generate is not the same as what you started with. However, they are still equivalent. Does that make sense? They look different, they operate differently as a graph, but they still have solutions that were the solutions of the original. And that's a concept that we need to be kind of cautious of and leery of. All right, so the addition property equality. Addition property equality, we're going to talk about four properties of equality here: addition, subtraction, multiplication, division. And the idea is that they're of equality. That means I'm going to start with something that is equal, and I'm going to do something, and we'll still get a result that is equal. Now, a result might be different than what I started with, but it's still going to be a true statement. All right? So it says adding the same amount, whether it be numerical or variable, meaning, numerical is just adding like 7 to both sides. Okay? Variable might be we're adding 7x to both sides. But what does x represent?
1.
It could be 1.
A real number.
A real number. So it could be 2, it could be 3, it could be 4, right? So if it's 1, I'm adding 7 to both sides. If it's 2, I'm adding 14 to both sides. If it's 3, I'm adding 21 to both sides, right? So even though it's a variable component or a variable term, because x is a real number, I'm really just adding a number to both sides, right? Does that make sense? Okay, so that's something to keep in mind. Okay? When we're adding something to both sides, and we produce an equivalent equation, that's using the addition property equality. So it says if A is equal to B. Okay? So you got two different things that are equal. Now, when we talk about just numbers, it's like 3 equals 3 or 5 equals 5. But talking about maybe equations with variable components, it might be like 2x equals 10. Okay? So 2x equals 10, those are visually different things, right? 3 equals 3, those are visually the same, right? Does that make sense, everybody? Okay? So the reason, because some people asked last period, why don't we just call it A equals A if they're the same, right? Does that make sense? Well, visually they might be different. Okay? So that's why they use B instead of A equals A or B equals B. So since if A equals B, then what we can do is we can start with a third thing, C, and we can add C to both sides, and we still get something that is equal. Okay? So an example is just a very simple, basic example here. It says if 3 equals 3, then give me a number. 7. So 3, add 7 to both sides. Do I still get a true statement here? Is 3 plus 7 still equal to 3 plus 7? Yes. Okay. Now, it's a different amount. It's 10 equals 10 now versus 3 equals 3, but it's still true. And that's what we're looking for. Okay? And that's the idea that original equation, 3 equals 3, and my new equation, 10 equals 10, though they're different, they're still both true. Okay? Now, where we're going to see this used most is something like this. If x minus 6 is equal to 8, then x minus 6 let's write then plus 6 is going to equal 8 plus 6. Does that make sense to everybody? Did I add 6 to both sides? Now my hope is that you realize why I added 6 to both sides. What is negative 6 and positive 6 together? What do we call those? You guys remember? Okay, they're opposite numbers. Okay, but they add up to 0, which they're called what then? You said it. Inverse operations. So adding, subtracting, inverse operations, but if we have the number with it, we call those numbers additive inverses because they're going to add to give me 0, right? And that's what we want. So understanding, though, that I add the same thing to both sides like I did here or like I did over here. So then when I do my order of operations and I look at negative 6 plus 6, what's negative 6 plus 6? 0. So it leaves me x minus 0 or x plus 0. And over here it leaves me 14. So it tells me then that x needs to be 14, right? Does that make sense? That's the idea. So that x equals 14 is still, it's a new equation. It's different than what I started with. X minus 6 equals 8 is different than x equals 14. However, they're equivalent equations because their solutions are the same. Is that okay with everybody? Okay. I want to kind of show you something real quick on how these things behave. And we'll learn this, but this is a very, very, very important thing as we work through algebra. And this is what I was trying to tell you about my college algebra students, trying to recognize this and realize this as they're working through problems algebraically. When I had, what did we start with, x minus 6 or x minus 6? So that's the line. If I were to graph it, that's the line x minus 6. And we'll get practice at doing that later on. And I'll show you how to use this program and everything as well. And then we had, y equal, we had, on the right-hand side, we had 8, right? So does everybody see here? So I had x minus 6 equals 8. So all I do here is I graph the left-hand side, x minus 6, and I graph the right-hand side, 8. Does that make sense? Every time you deal with an equation, this is the graphical application that's going on behind the scenes. And when we solved that, we got 14, didn't we? But you're seeing that that's the x value of the point where those lines intersect. Does that make sense to everybody? Okay. So whenever you solve an equation, my hope is that we start to learn that the left-hand side of an equation is going to have a graph. The right-hand side of your equation is going to have a graph. The answer to those equations is where the graphs cross. And it's the x value of where they cross. Okay? So we went through a little bit of work, and we ended up with the line on the left-hand side. So now I'm doing this one here. The left-hand side is x, and the right-hand side is 14. Okay? Now what I need you to understand is that this graph over here, the one on the right, that is different than this one, right? See how this red one here goes through, down here would be negative 6. Here it's going through the origin, right? This line here is going through a height of 8. Right now it's going through a height of 14. But if I look at the solutions, click on them over here. If I look at that line and that line intersecting, they intersect at B. What's the x value for B? It's 14 again, right? Just like it was in the first equation, x minus 6 equals 8. Is that right, everybody? Does that make sense? If you can wrap your head around that and understand, and it'll make a lot more sense, guys, when we get more complex graphs, and I can show one graph on the left that then looks entirely different than the one graph on the right, but they're going to share intersection points that have the same x value. It'll make more sense. But every time that we see a new type of equation, I'm going to show you something like this because I want you to gain that logic, that understanding. Because let's say this: we get to the ACT, maybe we get to end of course exam, whatever. We get to a test and I forget how to solve an equation. but I have a calculator in front of me that allows me to graph. If we can use that idea to graph the equation and look for where they cross, then I've got my answer. Does that make sense? Okay. So this morning this happens every year. I give my first period a test or a quiz today had 7 questions on it. And both periods, the students were sitting there, and it took them the whole period, and they're sitting there, they're beating their heads against their desk, like, I don't know if these answers don't make sense. They don't make sense. They don't look right because they're weird numbers. They're not coming out to be real nice, pretty numbers. They're just really ugly, real nasty decimals and radicals and all that kind of stuff. And I do that on purpose because I've been telling them, before you do anything, because they know how to graph things real well, and you guys will too soon, that before you do anything, graph the equations. Because if you can graph them, you can find the solutions. So you should know what the solutions are before you do any math. Does that make sense? But of those 35 students, nobody was doing that. Okay? Isn't it much easier to do something if you know what the outcome's supposed to end up looking like? Yeah. Okay? Or maybe it's so much easier to be assured of your math if you know what you're supposed to get. Okay? So that's kind of an approach that I hope that we kind of pick up on eventually. Okay? The next property is subtraction property equality, which is really the same thing as addition property equality, because subtraction is adding the opposite, is it not? So anytime that we have an addition property, we're going to have a subtraction property because addition and subtraction are the same thing. Okay, so subtracting or adding the opposite. Okay, so subtracting the same amount, whether it's numerical or variable again, to both sides of an equation produces an equivalent equation. So there's the same structure. If I start with 2 things that are equal, you're starting with that. That's the equation in front of you. 2 things that you know for certain are equal. So maybe it's like 10 equals 10. If I have that in front of me, then take a third number, C, and you can subtract that from both sides. Do you still get something that is equal? Okay, so if A equals B, then A minus C, subtract C from the left-hand side, subtract C from the right-hand side, B minus C, that result should still be equal. Okay, so we have an example there with just real numbers. Okay, those examples, sometimes people think, well, those are kind of basic, elementary, maybe even trivial. These are the ones that maybe you have familiarity with. If I have X plus 10 is equal to 15. Okay, so what they're saying then, that there is your A. Does that make sense? This here is your B, and that's why they use A and B, is because if I look at the X plus 10 equals 15, they're visually different, like A and B are visually different, right? Okay. You guys understand what I mean when I say visually different? They do not look the same, right? They're not cut and paste objects. But if I start with that, I know that that's true because that's what I'm starting with. That's in front of me. Let's add something. Sorry, let's subtract something from both sides. What do you want to subtract from both sides? Okay, the logical thing is to take and subtract 10 from both sides, right? So minus 10 equals then 15 minus 10, right? If you do order of operations, then order of operations tells you to do that, and we recognize those are, again, additive inverses. So that gives me X plus 0, and then I do that, and it gives me 5, right? You guys remember doing that kind of thing, right? Okay. When I write it there in red, most of you, we talked about this in the last class, because I want to write it the way that maybe you'll see it in other publications from time to time. But you guys probably are more comfortable with doing this. Is that correct? Okay. Now, what I want you to understand is that there really is still an equal sign there between the negative 10 and the negative 10. Because we're guaranteeing that what we do to the left-hand side, we do to the right-hand side. So it's got to be the same amount. Okay? Like I have a scale. You guys have seen those balance scales, right? Where they've got like something like this, where we've got a plate here and a plate there, right? Yeah, like the Justice System's Lady Liberty, right? Okay. So if I put something down on this, that's going to go up, right? So if I want to keep my scale balanced or my equation balanced, if I put something on this side, I've got to put the same thing on that side so it doesn't get heavier on one side, right? The same thing happens if I want to remove something from the left-hand side. I got to remove the same from the right-hand side. Okay? So I got to be able to keep that balance, and that's what this is doing here. Okay? So when we start the procedure for solving, and we've already done a couple, okay, but the procedure for solving some of these equations, and this is all equations throughout the entire year that we're going to see until about probably beginning of March, okay? Right now, we're going to have to isolate the variable, okay? When I say isolate, that means to get by itself, right? Okay? We're going to isolate the variable, get it by itself. We want our variable x. So we're going to say eventually solving for 1x. Okay? Trying to solve for 1. Trying all the things that I teach you here in a little bit, or remind you of, I think you know a lot of this. You're trying to get 1x by itself. Okay? And these steps, these procedures are going to help us do that. It says in order to isolate the variable, we will use properties of equality and inverse operations to do so. Okay? Meaning that I'm going to add something to both sides. Okay? Or I'm going to subtract something from both sides. And that thing I add or subtract needs to be the same on both sides. But what I choose to add to both sides, or what I choose to subtract from both sides, is going to be determined by inverse operations. Looking for, ultimately, additive inverses. Okay? Just remembering our inverse operations. Addition undoes subtraction, subtraction undoes addition, multiplication undoes division, division undoes multiplication. So what we're looking at here is just some examples. These should be pretty straightforward. If I have x plus 10, let's go 12, is equal to 30. Okay? What are you going to, you want to be able to do something to both sides, right? If you want to add 100 to both sides, by all means do it. X plus 112 is equal to 130. That works. That's fine. But did it get x by itself? Did it isolate x when I add 100 to both sides? No. Okay? So even though it's fine, I abide by the property of equality there, it's not efficient. It's not going to get me to the answer the quickest. I look at that positive 12. And now I'm saying, okay, positive 12, I need to use inverse operations. What is the inverse operation of plus 12? Minus 12. So I'm going to subtract 12 here. And now what I do on one side, I have to do the other side. So that is the subtraction property of equality. Okay? Now if I look at that, x plus 12 minus 12, that's just going to give me x plus 0, right? Did that end up giving me a 1x all by itself on the left-hand side? Yep. And now I got to do the work on the right-hand side. So I got 30 minus 12, which is 18.
Wait, couldn't you just do 12 minus 2?
Say again?
Instead of doing this back, couldn't you just do 12 minus 2? Like instead of doing 12 minus 12.
Oh, you go 12 minus 30, you're going to get negative 18. I see it. You're just doing it in your head real quick, right? And you're saying, okay, I'm going to take the 30 and 12 and subtract them, right? Yes, that's fine. But my thought is, let's try not to do a lot of stuff like shortcut tricks early on, because eventually if we do a bunch of shortcuts and tricks and try to remember those things, down the road they're going to cause us problems. Okay? So just subtract 12 from both sides there, and we've got our answer. Now, what is nice about every algebraic equation you ever come across? You should be able to take your answer And if x is equal to 18, I should be able to plug my answer in right there for that x. And I should be able to say 18 plus 12, does that equal 30? And that, when that's a true statement, that guarantees me that I've done things correctly. Okay? If I were going through here, let's say I go through here and I accidentally do it the wrong way. I get negative 18. And I plug that in, I get negative 18 plus 12. Well, that gives me negative 6, right? Does negative 6 equal 30? No, so that tells me that negative 18 is not the right answer. Of all the numbers that exist, there is only one solution, one value I plug into x that makes this statement true, and that's the value of 18. Let's do this one. Let's go x minus 15 equals 45. X minus 15 equals 45. What do I need to do there? Okay, add 15. Okay, so it's minus, so I need to use the inverse. So the inverse is addition. And I'm going to get 1x equals 60, right? Okay. What if I did, let's do one of these. Let's go x plus 3 minus 4 equals 7 plus 12. What you're going to learn, and this is something that piggybacks off of what we talked about with order of operations, what you're going to find out with solving equations is most times they're going to tell you on both sides of the equation sign, try to find those types of things right there. Now, the things I just highlighted are called what to one another? Like terms. So they're going to tell you to combine like terms first. Okay? So if I did that, what's positive 3 minus 4? Negative 1. So I'm going to rewrite that as, so the x I didn't touch, this becomes negative 1, so I'm going to write x and then minus 1. What does that turn into?
Add 1 to both sides.
19. Okay? So now I look at this, x minus 1 equals 19, and now you're going to say, well, I want to get x by itself. I need to isolate that. So I'm going to use the inverse operation. Add 1 there, add 1 there. Gives me x equals 20. Okay? And that is perfectly fine. You can do that. No issues there. However, and this is what people sometimes struggle with, is that every equation I give you, there's an infinite number of ways of solving it. Okay? There's always one efficient way, most efficient way, but could I have added 15 to both sides there? And then subtracted 7, and then added 30, and then divided by 2 to both sides? As long as I do whatever I want to do to both sides, I'm going to keep my equation balanced. Okay? However, if I added 20 to both sides and subtracted 3 from both sides, that's not going to isolate x very fast. Okay? But this is an approach that is fine to use. If I go like x, I have minus 4 plus 3. Plus 3 minus 4. Plus 3 minus 4 is equal to 7 plus 12. Okay? Did anybody think about maybe subtracting 3 here and subtracting 3 over there? What's positive 3 and negative 3 going to give me? 0. So now I'd have x plus 0 minus 4, which is just x minus 4, right? I'm going to keep writing this as that. But this is showing that I subtracted 3 from both sides. Anybody think then, well, I can add 4 here and add 4 over there? And that's going to give me 0, right? So I got 7 plus 12 minus 3 plus 4. What's 7 plus 12? 19. Minus 3. 16 plus 4? 20. Okay? So even though they tell you you should combine like terms, they're doing that because it should eventually in the long run save you some steps. Instead of having to subtract 3 and add 4 to both sides, If I combine those like terms, all I've got to use is use the addition property equality one time. Here I use the addition property and the subtraction property equality, right? I subtracted 3 from both sides, and then I added 4 to both sides. If I combine like terms, I've only got to use one of those properties once. Okay? But that's fine. There's nothing wrong with that. Does that make sense to everybody? Okay? When we work with variables, okay, the number in front of a variable is referred to as the coefficient, right? Okay? It indicates a multiple of the variable. It indicates how many times you are ultimately adding that variable together. Okay? So if I have something like what, 3x, that really means x, right? Okay? If I have, 5 over 2x, that's 5 halves, or 2.5x, okay? What that means is I'm taking x plus then half of an x. Does that make sense? Okay? So that number out front is a multiplier. It tells me how many times x is being added to itself. Okay? We see the multiplication property equality. It says multiplying each side by an equation by the same non-zero number, meaning we don't want to multiply by 0. Because I multiply by 0, what's everything go to? 0. It gives me 0 equals 0, and that's trivial. It's a boring equation. So we want to make sure that the number we multiply by is not 0. When we do that, it produces an equivalent equation. So this property makes most sense to use when the coefficient is a fraction. So I'll show you some examples here. It says if A equals B, then just take any number of C that you want, multiply both sides by it, and you should have still a true statement. So if I have, let's say 3 equals 3, then taking 3 times 4, does that still equal 3 times 4? Does that make sense? I think, and this is how every algebra class is taught. I think in my personal stuff, I'm sitting in the classroom as a high school student, and you write 3 equals 3, and then write 3 times 4 equals 3 times 4. I'm going to look at you like, well, yeah, you idiot. That makes sense. Okay? But the reason we talk about it that way is so that when you realize what you're allowed to do here tells me then, well, when I have x over 2 is equal to 3, then, okay, well, what's the idea here? Well, x over 2 is telling me that I've got some number, I don't know what it is, being cut in half, right? And I want to solve for that x. What I need to do here to get that thing cut in half, or the thing that is cut in half undone, I want to get that 1/2 undone. Does that make sense? Yeah. Okay. So what do I need to multiply to get that 1/2 undone? The reciprocal. So what's the reciprocal of 1/2? Okay, so be careful here. 2 over 1. So we only want to talk about the coefficient. So we know that x, I'm just going to write it over here. We know x over 2 is equivalent to 1/2 times x, right? Those are the same thing? Do you guys know that? Okay. So the coefficient of the x right here is just 1/2. So then I multiply, like you said, by 2. So then if I have 2 times x over 2, that's going to equal 3 times 2. Just multiply both sides by 2. So now, this is going to give me, when I multiply a fraction times a fraction, it gives me 2x over 2, right? What's 2 divided by 2? 1. So it gives me 1x equals 6, right? Now think about this. Plug this back into the original. What's 6 divided by 2? 3. And that's true, right? So when we're dealing with, and I want to come over here because I think this is important as well to understand this. We said x over 2 was equal to 1x over 2, which is equal to 1/2 times x, right? These are all the equivalent representation of one another, and I want to actually start with this one and work towards the other two. If I have 1/2 times x, okay, that's what this is saying, right? what does x represent? A number, right?
Real.
A real number. Can I take any real number, any number you want, and put it over 1? Yeah, because I take 15 and put it over 1, I still got 15, right? Take pi and put it over 1, you still got pi, right? Now what are you going to say? Okay, I keep it small, yeah. Okay. But if I have x, which I don't know what it is, can I put it over 1? Yeah, so that's like the 15 over 1, 12 over 1, 30 over 1, whatever it is. Do you have a fraction times a fraction here?
Yes.
Do you multiply straight across the top?
Yes.
Does that give you 1x?
Yes.
Straight across the bottom, does that give you 2?
Yeah.
If I've got 1x, do we usually write that coefficient?
No.
No, we just leave it alone, right? We take it away, and it's an understood you only got 1x there, right?
Yeah.
So does this show you that if I start with the 1/2 times x, that I can rewrite that as x over 2? Just because of how we multiply fractions?
Yeah.
Okay? So that's something important. And that's because you said, Annika, that we have to multiply by reciprocals, right? It's going to be very important for us to recognize what those reciprocals are. Okay? So if I have, something like this, 1/3 x equals 4, what's the reciprocal there?
3 over 1x.
Okay, so 3 over 1. Now, careful. I only want the coefficient reciprocal, or the reciprocal of the coefficient. So leave the variable alone. That's just there for the ride. Only want to multiply by the 3 over 1. So I multiply by 3 over 1, what do I come over here and do? 3 over 1. The reason we do this here is multiplying fraction. What's 3 times 1? 3. What's 1 times 3? 3. Okay, then on the right hand side we get 12, right? So what's 3 over 3? 1. So we get 1x is what we're looking for, right? Okay. So that's, I don't want you guys to, I don't want to give you a rule that says, oh, if it's a fraction, multiply by the reciprocal. I want you to know why. Because when I multiply by a reciprocal, it turns my coefficient into 1 because of how we multiply by fractions, right? Huh? Yeah, what's 4 times 3? The top part, that was the original equation. Right, so here I was doing, so we multiplied this here, got that 1x, right? And then 3 times 2 gives me that 6. Yeah. Wait a second. So the next thing I want to talk about is something like this. Like if I have like 2/3 times x equals, let's just say 1/2. Okay? You guys have probably been taught in other classes because the 2/3 and the x are stuck together using what operation? 2/3 and x, or how are they stuck together? What operation? Are they being added together, subtracted together, multiplied, divided? They're being multiplied, right? And then you say, okay, well, how do I undo multiplication? And they say division, right? And then you get to the stage where you say, okay, well, I'm going to divide both sides by 2/3. And that is absolutely correct. You can do that. Divide both sides by 2/3. What's 2/3 divided by 2/3? 1, right? And I get 1x. But then over here, I got to do the same thing, correct? So what is 1/2 divided by 2/3? And now we got to ask ourselves, how do I do that math? You guys remember how to divide a fraction by fraction? Say again? Okay, so you're saying keep this one, switch this one, and do that. Okay? So now, and that's what I want us to start avoiding, is those types of phrases. Because we forget what they are, right? We forget what they mean. I want us to understand why we're doing this. If I take 1/2 divided by 2/3, and I multiply 2/3 by 3/2. Now the reason I want to do that is because what is 2 times 3? 6. What's 3 times 2? 6. What's 6 over 6 turn into? 1. Okay? Now let's look at the top. I got 1 times 3. I've got 2 times 2. Okay? So this gives me 3/4. What's 3/4 divided by 1? 3/4. Okay? Now, here's the reason we did that. What this is, when I multiplied here, this is still a fraction. It's 3/2 over 3/2. What's 3/2 over 3/2? 1. So, when I take 1/2 divided by 2/3, all I did there is multiplied by 1, right? So I didn't change the amount. But the practice there actually produces a better representation of what 1/2 over 2/3 is. It's 3/4. Does that make sense? Okay. I don't know. I've never heard that before, actually. Yeah. So when I have 2/3 x equals 1/2, okay, instead of going through all that stuff, the idea is, instead of dividing both sides by 2/3, let's go ahead right away and say, well, let's multiply this by 3/2, because what's that going to give me here? What's 3/2 times 2/3? 6 over 6, right? Or eventually 1x. Come over here and multiply by 3/2. What's that give me? 3/4 right away. Does that make sense, everybody? So I always get to, and I have all levels of students do this. When I have a fraction out in front of a variable, they say, well, let's divide by a fraction. I say, okay, do that. That's fine. That works. And then the other side ends up being a fraction divided by a fraction. I ask them, okay, now evaluate that. How do you do that? And they don't know how to do it because they forget that rule of dividing fractions. But if I recognize right away that I've got a fraction coefficient multiplied by the reciprocal, and it avoids us getting to that fraction divided by a fraction step. Okay? We will spend a lot of time on those, okay, in the future. The last example, or last concept I want to talk about is division. Okay? Division, property, quality. And this is the same idea. Start with two things equal, divide both sides by the same thing, and you still get two things that are equal. Okay? Now, what are you never allowed to divide by? You can never divide by 0. Anybody know why?
Undefined.
It is undefined. That's the result. Okay? When I say, does anybody know, hopefully the answer is no. I've just been told that, right? Hopefully by maybe next month or the month after that, we have enough math that I can actually demonstrate for you why you cannot divide by 0. It's actually pretty interesting, pretty useful process to go through. So that's math being backwards. You're told not to do something, but you don't have enough. You're told that like 5th grade, but you don't have enough math to understand why you're not. You just have to take somebody's word for it, right? Okay. This class is so math in general is trying to figure out those things I've been told in the past. Why have I been told them? Why do they really work that way? So it's the same. If I start with 10 equals 10, then 10 over 2 is still equal to 10 over 2, right? The place that we're going to see this the most is something like that. If I have 2x equals 8, what am I going to divide both sides by?
4. Oh, wait, 2.
I'm going to divide both sides by 2, dividing by the same c value, and that gives me x to be 4, right? Here's a question. If I have, like, negative 2x equals 4, what do you want to divide by there? Negative 2. And now you just got to remember, negative divided by negative gives me a positive. That's the reason I chose negative 2, because I want my x to be positive 1, right? What's a positive 4 divided by negative 2? Negative 2. Okay. What if I did negative 4x equals negative 16? Can I divide both sides by 4?
No, negative.
Why not? I did the same thing to both sides. Right?
Right number.
But you can do it though, right? As long as I do it to both sides, just bear with me. As long as I do it to both sides, I can do it. But what's negative divided by a positive? A negative. So I get negative 1x. And now you're saying it's not the right number because what do you want that to be?
Positive.
Positive. So now can I multiply by negative 1 or divide both sides by negative 1? Yeah. So you hear people say, I think Mr. Miller, when I had him, used to say chick boom or something like that. So you could get rid of this one as long as you get that one, right? Okay. But it's the idea that if I multiply this side by 1, I don't change the amount, right? But I want to change the sign, so I multiply it by a negative, because a negative times a negative gives me a positive, okay? There is a math Excel assignment. Should not be very hard. Have a great weekend.